Good.
Okay. Yeah.
Great. Excuse me.
Thank you, everyone. It's my honor to have the first talk today for the FedVision Workshop. And I'm going to be talking about privacy-preserving sensors for encrypted visual AI. This is a new topic that's closely related to federated learning for computer vision. A little bit of background on me. My name is Jeff Byrne. I'm the founder of a new company. It's focused on privacy-preserving visual AI. And one of our core technologies is really designing sensors, these new sensors that are privacy-preserving by design. So really, we work in the intersection of three areas. One is these encrypted visual sensors that I'm going to be talking about primarily today in this talk. We've also done large-scale data collections. These are consented data collections that collect personally identifiable information of subjects and videos that are, again, great relevance for the federated learning problem and real-time visual AI. So I'm going to talk mostly about sensors today. And some about the data challenge. For those of you who might be working on federated learning, but might be newer to the vision side, I want to give you a sense for just how broad the label space and the task space for computer vision is, and the risks involved with privacy. So let me show you a couple of videos. There's a vast diversity of activities that people can perform in videos. These aren't just simple things like waving, but also give you a sense for the types of things that people can do. They can do gestures around the house. They can do cleaning. They can put on their clothes. They can eat. They can drink. All of these things need to have data. They need to have videos. And especially with people, they have to have personally identifiable information of the people in them doing them. And they have to have labels on the sense of bounding boxes around the primary actor, the start and end frames for activities, as well as some tasks require things like masks around objects. And some more complicated tasks need things like understanding of an entire scene of a complex activity. So diarization of a full complex long video. So not only are activities very diverse, but also the spaces in which people perform these activities are also significantly diverse. So we don't just have one canonical location that we perform in our daily life. We've got our private spaces, our homes, our workplaces. And all of these have a vast array of different types of fine-grained objects and locations that we perform in. So all of the data that we need to be able to do activity recognition and other computer vision tasks needs to have this vast diversity of visual data. But all of them contain private information. These have things like things that might be in the background of these scenes that might be considered to be sensitive. So all of this data needs to be protected in a very careful manner. So similarly, all of the people that are in these videos are all unique. So there's a concern in the computer vision literature about collecting data of people that has not been consented. There was a big sea change around between 2018 and 2020 about there being takedown notices of computer vision data sets of faces that were available publicly on the web. They were scraped from the web. But none of the subjects in those data sets had given consent for their use of their personally identifiable information for the task of face recognition. So there's a need to be able to collect this type of data in such a way that provides informed consent of the subjects who have their faces visible in these videos, so that you can always be sensitive to the fact that that your unique biometrics are yours alone. And finally, I want to say that not only are the tasks that I've presented so far, things like activities and spaces and identities, all a big challenge for computer vision, there's also the compositionality of trying to compose together these identities and objects and activities into larger and larger, more complex scenes that require scene understanding. So I want to give you a sense for just the vast space of the labels that need to be collected in a computer vision task to be able to enable something like federated learning. Right? And I'll say that all of this data that you've seen so far has been collected by our company. One of our core capabilities is collecting large-scale consented data from subjects around the world. And I'll talk a little bit about how that relates to the federated learning problem. But before I do that, I want to take a step back and talk a little bit about data privacy laws. And this is, again, of relevance for federated learning. This is going to be a little bit US-centric for those of you that might be attending CVPR from abroad. But you might be familiar with in the EU, the GDPR. In the US, there's state-level privacy laws in California and Illinois. But one thing that you might not be aware of is that there is a federal law that is currently in discussion mode. That's there's been draft language released for the American Data Privacy and Protection Act. This is what's considered to be the American GDPR that was just released about 2 weeks ago. And what this means is that in the US, it's going to be much more difficult to be able to collect labels and collect data from individuals without getting their informed consent. And also being able to provide what they call data minimization, is only doing the types of operations and only collecting the types of data that are the smallest amount of data you need to provide your service to an end user. And most importantly, there's language in this draft for to be able to provide a way to sue companies, to be able to get financial compensation if you violate their privacy. So I wanted to point this out, given that this is very new. There's still discussion. But this affects everyone in this room who wants to do federated learning in private spaces. There has been a lot of discussion about in the past 2 years about different versions of the American GDPR, but this one has bicameral support, and so far has been it's made it quite far in the discussion phase. So I wanted to point that out for those who might not be aware of it, that this is coming, and those of us in the privacy world say that it can't have come soon enough. So what's one of the most important things that you need to get in order to provide privacy-preserving visual AI? And that is consent. This is an example that was generated by my colleagues when we were doing face recognition work of a gigapan image. Gigapan is a very ultra-high resolution image of a scene where you can zoom in on different portions of the scene and identify individuals. We did that. We tried this. We took this gigapan image and generated face detection on this. And you can see this is from Barack Obama's 2008 inauguration. And you can see that you could use this for identifying all the individuals who happen to be in the scene. But none of these subjects have given their informed consent for how their personally identifiable information in this image is going to be used for the task of something like face identification. So it's important to be able to get this type of consent so that when your face is present in a video, that you as the individual, the owner of your own face, have the ability to control when and how your data is being used. So it's something always that's very important to keep in mind for those of you working in federated learning. So one thing I want to talk about is what I like to call the dark domains of visual AI. So in the introduction, we heard about things like medical applications, taking medical images of subjects that are subject to HIPAA law, HIPAA data privacy law, and that's a fantastically good application. But there are also applications of visual AI that I like to call personalized monitoring or ethical security, where you can imagine having security cameras spread around our private or shared spaces, where we want to be able to do things like personalized monitoring or ethical security without violating any of this privacy. But in a lot of these cases, there's not enough data to be able to take advantage of these sensors. So there's a limited amount of data for things like security cameras, but we don't have enough data of the diversity of people and the diversity of locations. We don't have any cameras that are in your home, because who wants to have a camera watching them at 24 hours a day in their own homes? But we might want to have the benefits of something like visual AI in our private spaces. So these dark domains are either a data source or a task that is not exposed today to visual AI due to these privacy risks and due to the fact that it might not perform as well as we need it to, or that we just don't have any data sets. I'm interested in these types of domains where we haven't explored and deployed visual AI because of these types of limitations. So let's ask the question: is it federated learning to the rescue for this problem? So can we take advantage of federated learning to address the problem of the dark domains of visual AI? So as we heard in the introduction, the federated learning problem is trying to do distributed learning on these decentralized data sets on these edge devices. Some of the challenges that we might face are trying to address this long tail of private labels and these diverse tasks. So let me come back to this and say that here are some examples of the long tail of human activities. This is a data set that we've collected of just around the house of people performing activities of daily life. And there are very common labels that are present for activity recognition, things like standing up or talking to people that are very commonly occurring. But there are also very uncommonly occurring data, things like falling into a pool or spilling things on the floor, or interacting with pets. All of these things, I mean, even if you were to set up a camera and have this data available to you for federated learning, the infrequency of getting these labels in this data stream means that even if you were to watch for months and months and months, you might only get a few examples of some of these uncommon labels. So how do you deal with the data imbalance of this problem so that you can actually do learning at very large scales? So I'll give a shameless plug for some of the work that we're doing on this in this space about trying to do consented data collection of people, where we've collected over 1.5 million videos, all consented of subjects performing activities of daily life, recorded from a third-person perspective, and all open data sets. So unlike the federated learning problem, where we're trying to keep the data close to the sensors, we've gone the exact opposite, which is give the data out to everyone so that it's publicly available and it can be used to address this long tail of tasks for activity detection. So this is a workshop that's currently in progress, if we're being planned out for 2023. And we're quite excited about the capability of doing this collection. And the way that we do this is by designing a new platform for data collection. This is a mobile application you can download today from the app stores, where we give this to third parties where in this case, a third party might be a freelancer around the world. We've collected from over 30 countries and over 130 cities, where we give this to them and we ask them to collect a video of these rare, infrequent activities so that we get lots of labels of the things that are uncommonly occurring. So we're actually engineering the incentive to get the types of labels that we need for the visual AI task. Okay, and this is something that you can use today to be able to collect custom on-demand video. But I want to come back to this idea of the challenges of federated learning. We talked about the long tail of private labels. There are lots of infrequent data that we need to be able to do these tasks. We've also got label deficiency. This is the problem of that in order to get opt-in consent, we need to have individuals who own these sensors allow us to do training on their data. So that in the federated learning sense, you've got these distributed sensors, they've got data streams coming in, but somebody has to label this data. Is it going to be the end user? How do you incentivize these end users to say, yes, I want to label the boxes and times to do supervised learning, or to be able to say yes or no, this is it made a mistake or it didn't, to do something more like self-supervised learning. So that requires opt-in consent, and getting that data is very difficult for the federated learning task. So we've also got challenges of, as I mentioned, getting informed consent, data poisoning attacks on these edge devices. But the most important one that I personally believe is critical for privacy preserving is weak privacy guarantees in use. So what this means is if I have a sensor that is viewing, say, this room, I might be able to do federated learning on this data and from this camera in this room, and then generate gradients that I can send to the cloud to be able to do federated learning of a model where we do weight sharing. But the video that's collected from this sensor is still prone to attack. While the gradients are being computed on the edge device, there's an image that's formed. And that image can be exploited by an attacker. If an attacker got access to the network in this space, they can extract those videos, and that destroys your privacy. So how do we maintain the privacy of a video when it's being used for the task of federated learning? And that's where encrypted visual sensors really comes in. So let me give you an example. Visual scenes really contain a lot more information that's what's needed for a task in machine learning. Say, for example, you want to do a task of person detection. It's straightforward. There's lots of data sets, even consented data sets for doing person detection. But this image here contains more information than what's needed for just that simple task. There are things like passwords on the wall. There's private information on the screen of this computer. There's a non-consented subject that happens to be walking by in the background. And all of these bits of information are embedded in the pixels of this image and these videos. So how do we construct a sensor that doesn't leak this type of private information, at the same time allows you to perform the machine learning task that you want to do? And that's really the holy grail of privacy preserving visual AI, which is an end-to-end encrypted process where this sensor generates an encrypted output. You do processing on that encrypted data, generate an encrypted result, and that encrypted result gets sent to the end user. So at no time are pixels exposing private information. And that processing chain can be used for things like federated learning without exposing the raw pixels in here that could destroy your privacy. So I might ask the question now, can a sensor be optimized for an AI task without human interpretability? So this is a paper that we published a few years back with our colleagues at Rice University. Where a conventional vision system has a scene, you go through some optics, you generate some analog preprocessing, and then you generate an image, a measurement image. But if and you can do tasks on that, person detection, face identification. But if an adversary gets access to those pixels, they can tell who that is, and that destroys your privacy. So we asked the question, well, there's lots of ways of designing sensors that are more kind of precise to the task than a camera. Let's say, for example, that you have the sensors that are in bathrooms that can know if you walk in, just trying to do motion detection. You can generate a motion detection by putting a camera into those sensors, but that generates a lot more information than you need for the task of is there motion in this scene? So we asked the question, well, can we degrade these images in such a way that we can still do a task, let's say face detection, but we can't do face identification? So how do you degrade an image so that you can perform one task, but you can't perform a more precise task? So if an adversary were to look at that pixelated image now, they would maybe be able to say, it might look like a face, but we don't know who it is. So it preserves one form of privacy. The challenge is that there's a fundamental trade-off here, that if we do this, and we went through this exercise of enumerating the types of degradations, the quantizations, the different types of convolutional masks, the different types of analog preprocessing, gains, biases that get applied to an image. We tried all these and we found that there was a clear trade-off, that as you make the image more and more private, meaning that you can't have it interpreted for an identity for an adversary, the performance on the primary task, in this case, face detection, went down also. So that's not what we want. We wanted to say maximize our task on face detection, but minimize performance on face identification. That's the ideal performance in the bottom right. But everything that we tried was really on this trade-off of privacy versus utility for the task. So how do we do better? This is really where encrypted visual sensors come in. And I just want to mention briefly some of these design requirements. So we want to make a sensor that's image-free, doesn't generate images that are human interpretable. It's encrypted in the sense that the images generate this transformed pixel measurement that can be processed by visual AI without ever recovering the original image. And I'm going to talk about how we do that. And finally, there's an interesting design space here about optimizing visual sensors for the AI task. Right now, all of the visual sensors that are deployed in our common spaces are all really designed for human security analysts. The locations, the frame rates, the resolutions, the gains, the fields of view, all of them are optimized for a security professional or an expert reviewing those videos for the task of forensic analysis. But what if we can design this now for AI to view these sensors while preserving an end-to-end privacy? So there's a lot of interesting games you can play once you remove the human from the equation here. So this is the last. This is the key idea that I want to present for this talk. Privacy preserving sensors, these are these encrypted visual sensors, create these private videos. We have a paper that we published at BMVC recently that addresses this problem. So we call this problem a Keynet. And a Keynet is you specifically couple a visual sensor with a machine learning system. They're one-to-one coupled, so that a sensor that generates a particular output is keyed to a machine learning system. We call this machine learning system a Keynet. And this can be a general convolutional network that does a task like activity detection, face identification, face detection, and so on. Any task that can be done by modern machine learning tasks. So the sensor outputs this bit. If you can see my cursor here, it outputs this kind of noise output. But if you design the machine learning system in a very specific way, we can generate encrypted inference results without ever recovering the raw pixels for this sensor measurement. We can generate an encrypted inference results that can then be given to the owner of this sensor so that they can decrypt it for end-to-end privacy. So what we're interested in is trying to generate these custom vision sensor outputs that can be deployed in a room like this, such that if an adversary were to get access to the camera, to the network, or even into the hardware of this sensor, what they would see is this image, this noise image in the bottom right. But that noise image can be sent to a third party, say a cloud service that does our visual inference. We do the processing of that image and generate an encrypted vector. At no point do we need to decrypt this video, but we can generate this encrypted output, and then that gets sent to the end user for decrypting. So things like activity detection outputs. We can generate lots of these sensors and lots of these different machine learning systems, and each one is one-to-one paired. So you can't repurpose a sensor for another task. It's locked into a particular task. Okay. So how does it work? The keys are in the paper, but I'll kind of give you the flavor for how this works. In a conventional convolutional network shown on the left, it's a sequence of linear and nonlinear layers, where the linear layers do things like convolutions or matrix multiplications. Nonlinear layers do things like rectified linear units and other nonlinear transformations that go into a sequence of dimensionality reductions all the way to an inference result, which is some vector of things like some regressed output, regressed boxes, label predictions, softmaxes, and so on. What we do is we generate these private transformations of the weights of a convolutional network, such that what gets input into the image, into this convolutional network, is this keyed image, which is a linear transformation of the raw image by this unknown matrix, sparse matrix A sub naught. And then that gets passed all the way through this convolutional network, such that at every stage of the processing, the weights that are encoded in this network are all encrypted by these red matrices A sub k, and the inference result is also encrypted along the way. So the keys that we really need to preserve that are private are these ways that we transform the weights and transform the images prior to them being input into the system. And what this means is now that if I were to give a raw image through this traditional convolutional network, I generate some inference results here. I can take the same image, encrypt it, pass it through the Keynet, and I get an encrypted result that are related by this unknown inverse matrix. And that is a private key that only we know, that only the end user knows for decrypting this output. So this is end-to-end privacy now that does not require any knowledge of what's in that noisy pixelated image. Okay. I think I'm going to skip over this one. The details for how we construct the requirements for this optical transformation, the details are in our paper. So I want to show what this looks like. So we went through this design requirement, and we determined that a feasible transformation here that is a way of transforming these images in such a way that you can do privacy-preserving encrypted visual AI is what's called a generalized stochastic matrix. And this is a matrix that includes fractional pixel shuffling. You're taking shuffled pixels and moving them around in a permutation, as well as an analog transformation that adds a gain and a bias. This is all linear. This is a linear transformation that transforms the geometric the geometric location of pixels in the optical axis, and the photometric variation of pixels on the analog axis. And because what we designed this to do, we designed this to be implementable in optics, because this is all linear. We don't require nonlinearities in the optics. We can do this before there's any sensor measurements, before the CMOS sensor. This is all implemented in optics and implemented in the analog preprocessor before photons actually get read out from a CMOS sensor. So even if an attacker were to be able to actually inspect the CMOS digital outputs after the A to D converter, all they would see is this noise in the bottom right. So this is truly privacy preserving, and gives you a way to actually control how much privacy that you want. You can go to something like full privacy, or something like what we like to call optical privacy glass, which you might still be able to tell this is a face, but you might not be able to tell it's me. Okay, so what would this look like? So let me give you an example here. So this is a quiz. The one on the right is the most private. The one on the left just really has this optical transformation, this permutation. You can probably tell that something is happening here, but because you don't know how this image has been transformed, if you were to look at this, the best you could probably tell is maybe it's a person. Maybe it's walking, there's some green here, maybe that's vegetation, maybe those are trees. The gray here, maybe it's roads, but hard to tell. So here's the raw video. So this is one that's never provided, never actually constructed by the sensor. But you can see that this is what it actually was. The middle image and the middle video and the far right video, those are what's processed by visual AI. That is the output of the sensor that would be observed by an attacker and is processed in this end-to-end manner. So humans can't snoop this, and it's really never decrypted, even during the visual AI processing task. Okay, and we can actually realize this in optics. We have our paper talks about a design technique called 3D optical, 3D printed fiber bundles that allows us to do this transformation in the pre-A to D conversion for applying this optical and analog transformation. A paper has a lot more details. All right, so finally here, I do want to kind of bring this back to federated learning. And talk a little bit about how what we've talked about so far would be relevance to security researchers on the federated learning applied to computer vision. So an open question in my mind is how do we do this distributed learning now on encrypted data? So a lot of the talks that I think you'll be hearing about today are about these decentralized data sets. These are decentralized. Jen, want to give me a hand here? Let me see if I can mute this. Good. Yeah, maybe that. Great. Good. All right. So a lot of the talks that you're going to be hearing today are talking about learning in decentralized data sets. So these are individual edge devices that have videos and labels, such that you can do processing on the edge device, share the learned models, and then aggregate them in the cloud, and then use that shared model as the federated learning output. But I talked today about the idea that the edge devices don't need pixels. They don't need to have raw data that's human interpretable. What if we were able to do distributed learning on these encrypted data, these noise images? I believe this is possible, but it's an open question for the research community. So if you're interested in that topic, please do reach out and we can discuss collaborations. The second major challenge is this issue of non-consented subjects. And this is a key aspect for the AD-PPA, this new privacy law that is currently in draft discussion in the US, where you need to get consent from every subject that has personally identifiable information, even if they randomly come into your video camera. though, if you were to do any type of AI processing on that, even if you're not actually trying to store any of their data, just processing them is something that can be a violation of their privacy. So how do you maintain the fact that you get consent from all of these subjects in these distributed data sets and decentralized data sets so that you only do the processing of those who have consented? It is an open question also about, in these decentralized data sets for federated learning, if you have subjects who want to opt out, who've given their consent but then want to opt out, but their weights, their information has been used to generate the weights of a federated learning output, how do you remove them from that? That hasn't been, that's something that hasn't really been explored in the privacy law space, but I think that that's something that is still an open question. And finally, we've got semantic security here, that on our website, we have a challenge problem where these are these encrypted outputs. There's a secret message in these images that you can try to crack. And if you can, then you can attack our encryption strategy. So this has been up for about 2 years now. Nobody's cracked it. So we're quite confident at this point that it's a secure methodology for this type of encrypted sensing. Okay, so with that, I'll pause there and thank you for your time and take any questions. Yeah, please.
So that's really great talk, and I just have a couple of questions.
Sure.
So one thing is for your use case, right? You already have inferred results, right? Encrypted. So how, because it's already encrypted, how do you verify your inference? Like accuracy?
Yeah, that's a key question. So that would be up to the end user.
Okay.
So the end user has the encrypted output. They're the only one with a key to decrypt it. So the end user is responsible for trying to provide feedback in terms of these labels. Our strategy has been that we train a model, a pre-trained model on our open data sets, rather than doing the federated learning strategy of relying on the end user, on the edge device to give us labels. We have huge open data sets that we collect using our mobile application that give us the label diversity that we need to train very large scale models from scratch. We assume that's where we do our validation. And but there's still a domain transfer problem of taking that learned model on that data, applying it to the edge devices, and then validating that. That is a hard problem, and that's still an open question to how we incentivize our end users to give us feedback to say yes, it worked, no, it didn't, and use that encrypted data for refinement and fine tuning of our models.
So another quick question would be, say for example, right, any video or like image is very feature rich. So for your use case, it's like your encrypted, the vector, right? Does it only contain like one set of feature, or you can have like multiple set of features? Say I have face detection here, I have some behavior detection here. Is that all combined to your encrypted vector?
What we're trying to do is have one network, one task.
Okay.
That you target a specific task for a particular sensor pair. Because what we want to avoid is being able to repurpose a sensor. Right now, video cameras are really designed to have, you can take an image and apply it to any task. But we'd like to be able to say there's a sensor that's specifically designed for one task, face detection, activity detection, and that it's targeted only for that task. But that's more of an engineering challenge about how we pre-train our networks for deployment rather than a scientific challenge about how to construct these encrypted vectors.
Cool. Thank you.
Sure. Yeah.
Hi, thank you so much for a very great talk. I have one question. So from my understanding about your talk, like you will So if you're just
yeah.
doing application on the client side, it only benefits for that user only, right?
Correct.
So all the people, they cannot have like the benefit of that data.
That's the hard problem here. That's the federated learning problem, which is how do you provide that type of feedback that's useful for the individual who owns that sensor and give it back to all of the other users. It has to be up to the individual to say, do I want to share my information, even at any granularity of privacy? Do I want to give it back to the overall community to be able to improve everybody? That should be up to me. And that is really the open question of this distributed learning on encrypted sensors. Since I don't want to give you my encrypted output, I don't want to tell you exactly what I did on a daily basis. But can I do learning on that encrypted vector? I think we can, but open question.
Okay, thank you so much.
Okay.
Yeah, I think it's a very nice talk about the much focused things kind of system. I do have one. So you mentioned for each of the tasks, you have specific encryption matrix, right? You can see that in one slide there. So you are saying for each particular task, there's dedicated network to do that. So is it in the future in the product line, are you trying to do maybe a single matrix can do multiple tasks, like multitask?
Yeah, that's very closely related to one of the first questions. But yeah, it is on the multitask side. It's something we could do. And that certainly makes it more efficient to have a multi-headed multitask network that shares a kind of encrypted backbone. We'd like to target one network, one sensor, but that becomes more of an engineering challenge about how do we deploy these sensors in practice. This is still in the research phase rather than the deployment stage. And we're still asking those questions to see whether or not our end users would like to have those types of multi-headed networks.
Okay, cool. So this just involves another one is how hard it is to build this encryption into the hardware.
Oh, it's very hard. But we have some work about trying to do 3D printed optics. It's actually it's fascinating just how you can do 3D printing, but of transparent diffractive materials. And there are devices that you can use to 3D print optics. Instead of having to grind lenses, you can actually 3D print these what they're called fiber bundles that kind of reorient where the pixels lie on an optical focal plane. So it's a big challenge to be able to design those. But once you design it, it's something that can be inserted into the imaging chain. So you take this 3D printed flat disk, insert it into the imaging chain right before the lens, and it generates this type of scrambling effect. But you need to know what that scrambling is so you can undo it as part of the visual AI processing. So this end-to-end processing is actually generated, that the keys are actually generated in the optics. So that process needs to be very precise. And that's where we are today.
Okay,
Okay, great. Thanks, everyone.